Hi, welcome back to Power Electronics Lectures. In this video, I'll talk about the structure of power electronics interface, which can be either one power electronics converter or a combination of more than one power converter. Understanding the structure of power electronics interface is so important, although it's very simple, because this will help us in the future when we go and design the power electronics converter based on a specific application. In any power electronics system, you'll find that we have four main parts. Number one is the electrical load. So here we have, let's say, electrical load. In power electronic systems, in my opinion, the load is much more important than any part of the system. It's more important than the converter itself. It's more important than the power source, and also it's more important than the controller. And here, so this is number one. Number two is the power converter. And within the power converter, you will find that there are a few components here. The main component in power electronic system is the switch, and this switch can be transistor, diode, thyristor, many other devices. We have capacitors and inductors mainly. Okay, and also we have the power source. So here we can see that we have the electrical, energy source, and we have the controller. Usually the controller will take information either from the input, from the source, and from the output, from the load, and according to this information which are taken from these the load and the source, it will give the converter the right decision to generate the pulse width modulated signals and many other things. Okay, so here, let's say this is connected here. This is given to the load. So these are power link, the green one, and let's say the blue one here are just information link or signals. Okay, so let's say this is number one, this is number two, and this is number three, and this is number four. This structure, the power electronics converter, let's say, can be either one of the two things. It can be either voltage link, voltage source, or current link or current source. The voltage link, when we talk about the voltage link or the voltage source, we mean we have a constant voltage source. So here we have a constant voltage. Okay, so this is the voltage, this is the current. We have a constant voltage source, and we have the availability or we have the option to operate at any current we want. Okay, so this is the key point in voltage source. If we have voltage source, that means we have a constant voltage, and on the other side, let's say the voltage is it has a constant voltage, and the load can be operating at any current. So we cannot say, for example, if we have a voltage source, we connect this voltage source to another voltage source. For example, we cannot design a voltage source converter and connect this converter to the grid, because the grid, for example, is a voltage source, is another voltage source. So voltage source and voltage source don't mix. Okay, So usually here we represent this voltage source by, let's say we have a grid here, okay? Here we have a converter. Capacitor means voltage source because the capacitor usually fixes the voltage, okay? And here we have another converter, and usually this is supplying a load, and this load of course can change its current, but it can be operating only at a constant voltage source. And usually here we have a controller, and as we said, the controller can take or give information to both the input and the output. So usually the voltage source is connected to a load. So here fixed voltage and on the other side we have variable current. Usually the grid side converter is to convert the line frequency grid voltage to a DC voltage, and then the load side converter it's different from any other converter according to the desired output voltage application. What applications we have? You can supply many applications. You can support many applications like DC or AC motor drives. You can supply power supplies, regulated DC power supplies, high frequency AC systems, induction heating, isolated DC power supplies, and so on. The current link usually used for high power applications or for high power levels, for utility related applications, because as we said, the utility related application is the grid, for example, or the network has a fixed voltage, so we need a fixed current to supply the fixed voltage grid. And the current link in general consists of thyristors circuits, and the current in them is commutated from one AC phase to another by means of AC line voltages. So here, let's say that we have a grid here. So this grid, in order to connect this grid to another grid or to supply another grid, we need current source converters. These current source can be either using thyristors, can be also using any other devices such as MOSFETs or IGBTs, but with a different arrangement. It's different than the voltage source. And usually when you talk about current source, this means inductance. You cannot say that we cannot connect a capacitor on the sending end terminal of the converter, because as we said, capacitor means voltage source, inductor means current source. And here we have another converter, and this converter connected to a load, not to a load, it's connected to another grid. So here we have grid connection. It's not very difficult to differentiate between the voltage source or the voltage link and the current link. You just you need to make sure that the output of the converter either be able to fix the voltage or fix the current. Usually if we fix the voltage, means the output should be connected to a capacitor, large capacitor. If what we mean to supply the current, then the output must be inductor, a huge inductors. Okay. Next video we'll talk about the switch mode conversion in power electronics systems. So see you next time.